Okay, we're back. So I forgot about this one here, story time with Dr. Shane. The story time there was really about the Possum Lake algae situation. Now the pictures I showed you were actually last summer, or I'm sorry, 2 summers ago, when I was putting this course together for the first time face to face. So the last time I was out there at Possum Lake, there was some algae warning, but there were no toxic algae warnings. So there's a little bit better situation here. Also, this slide is a little premature. There is something what are called thermal stratification in lakes that as the seasons change, well, you get, as the title suggests, strata or layers or levels of temperature that occur in lakes as time goes on. So that's there just to kind of make the point that these things change over time, and that's called thermal stratification. I may come back to that a little bit later, because to this point all we've been discussing is an oxidizing environment under fairly normal conditions. That is not always the case. Okay, this video or task is pretty simple. I want to basically go through balancing a couple of redox equations. Now here, I recommend that you really try this on your own. If you've studied your redox, so this is problem 10.5, and what we're showing is oxidation of ammonia to nitrate, so that should be enough for you to just get started. So it'll be NH3 as a reactant, nitrate, NO3 with a negative charge as a product, and you're told it's a basic environment. Well, okay, then that's the oxidation reaction, so what's the reduction reaction? And you're not even told what the reduction reaction is. You don't have to be told what the reduction reaction is because it's oxygen. So if oxygen is causing the oxidation, oxygen is then reduced, as we've discussed before. And in this case, it's reduced in a basic environment, and you already have that chemical equation from before. I really like this particular question because a lot of the water and a lot of the soils in the Cumberland Valley are basic. They have a pH, or tend to have a pH above 7. So I think I've seen pH as high as like 8.5 in some of the waters around here. So that's fairly basic. So this is a very practical problem, and if you're not in the Cumberland Valley in central Pennsylvania, you're somewhere else, what I recommend is, in addition to doing this problem, you could go and find, like say the water where you are tends to be acidic, and maybe do the same problem and see if you can answer the same question. I didn't write that one out. I might have put that on a homework, I can't really remember, but that would be a good one to do. And then here's the idea, is nitrates, let me give you a take-home message here. Nitrates, NO3 minus, that's the end of the line, if you will, for a lot of organic matter that contains nitrogen, which is a lot of it. Not just ammonia, but a lot of organic matter has nitrogen in it, and that's the final step. That's as far as it goes as nitrates. In fact, nitrates are one of the key indicators of water quality almost universally. That's important. And this infographic that I have over there, I don't have a whole lot to say about it because there's so much biology involved, which I'm not getting into, quite frankly. I won't call to discuss the biology of this, but you can see there, that's called the nitrogen cycle. There's so many of these infographics that we can look at that are helpful. The carbon cycle, the nitrogen cycle. So those are just useful sort of overall pictures, but we're going to stick to the chemistry, not the ecology and the biology as much, if you will. Okay, so that was a lot of talk. So let's just do problem 10.5. That's really the whole purpose of this video. And there are no calculations here, it's just balancing redox. Okay, so remember when we do redox, the way I show it is the method we teach in Gen Chem, which is called the half reaction method. If you use the oxidation number method with the book references in the appendix, that's fine. I'm not going to show both methods. I only do the other method in case if a student comes and says, I don't get this method, can you show me another one? So I'm just going to show this one. So remember, when we do oxidation reduction, We have an oxidation half reaction. We have a reduction half reaction. And then those two have to add up to your overall redox. Now, depending on when you had Gen Chem, oftentimes you had to figure out which one was which was oxidation, which was reduction. Here, we don't have to do that. We're told that it's ammonia being oxidized to nitrate. So we can use a little bit of chemistry common sense here. We're not starting from scratch. So if ammonia is going to nitrate, oxygen is literally adding on. That's oxidation, okay? And then might as well just fill this one in. So something has to be a reduction. And we already did this one. Oxygen is the reduction. So it's oxygen plus 4, and I think we said this is okay. My bad, I got ahead of myself here. I'm gonna balance this as if it's an acidic solution, and then I'm gonna turn it into a balanced equation in a basic solution. So this may be a little bit off from how you did it, and if the way you did it gives you the same answer, I'm good with that. So when we teach this in Gen Chem, we teach everything from an acidic perspective, because that's easiest, and then if it's in a basic solution, we just do a little trick at the end and turn it into the equivalent reaction in a base. So that's the way I'm going to do that here. So for now, let's just do an acidic solution. And if you do it differently and get the same answer, that's fine. Okay. So that's the chemical equation for the reduction of oxygen in an acidic solution. Let me double check that, which we did that one before. So let's go through and do the balanced one for oxidation. So the process is, let's see, what is it? We use water to balance the oxygen. There's no oxygen, so we have to put 3 waters here. Go over to the other side and balance the hydrogens using H+. There's 6, there's 9. And then we have to use electrons. So we have no charge over here, positive 8 charge over here, so we have to put 8 electrons there. And then we add these two together, the electrons have to cancel. So I'm going to multiply everything here by 2 to get the electrons to cancel. And then bring everything down, and we're going to balance this redox in an acidic solution. And then we'll do the final answer, which is what the problem was, in a basic solution down here. So let's just bring everything down. So we've got 1 ammonia reacting with 2 oxygens. Let's see. Okay. Waters. I think that's it over here. Because we're going to have 4 waters on this side and 3 waters here. So we're going to get more water there. It doesn't matter what we're going to put things in, by the way. Then nitrates. Make sure that's correct. Yeah, so just bringing the ammonia down, the nitrate down, water, there's 3 here, 4 here, so we have 1, but one of these cancel over there. 4, there's going to be 8 H pluses, so okay, so that looks right. Let's just double check it. Nitrogen, nitrogen, 3 hydrogens, 3 hydrogens, 4 oxygen. Yeah, okay, so that looks, and the charge is 0 on this side, and so that checks out. That checks out. Now, to make how do you go from an acidic solution to a basic solution? What you do here is this is the little trick. So this is acidic. So what you do is you add OH minus. Remember, OH minus means that's hydroxide. That's what you have in a basic solution. So what you do is you add OH minus to each side of the equation. So basically what you do is you neutralize the H plus and make it another water. So I'm going to add an OH minus to this side. But if you do that to that side, you have to do it to this side as well. Okay, just conservation of matter. So the final answer you end up getting, and then these two simply become another water. It's just acid-base neutralization. So in a basic solution, it's ammonia plus 2 oxygens plus OH minus goes to NO3 minus plus 2 waters. Check my notes. Yep. Okay, so we just did all the redox work. That's important to be able to do for any system that you're dealing with, whether something's oxidized, something's reduced. Okay, now what's the actual question asking? In what ways does this chemistry affect the acidity, basicity, pH of the water? Well, let's see here. So what's going on here? Let's not lose the forest for the trees. So when ammonia is introduced into the system, you're getting OH minus that's consumed. So the OH minus concentration goes down, right? So that's what this means. OH minus is consumed or reacted. Consumes makes it sound like a microorganism, but it's being reacted, it's being reduced. So the concentration, maybe that's a better way of putting it. So in this particular system, if this happens, if you introduce ammonia into it, in a basic environment, the OH concentration of OH minus goes down. Well, okay, which means it gets less basic, which is the same thing as more acidic, which is the same thing as a decrease in pH. Okay, that's an important reaction for the Cumberland Valley. One of the reasons is, this is what I was leaving was show and tell, I think. The next slide that I have is show and tell. This is a really good case study, especially if you have any experience at all with farming. On farm fields around central Pennsylvania, actually all over the country and world, you'll see giant tanks, and if you've seen them on a farm field or gone past them on your bike like I have, you get a whiff of this stuff, of concentrated ammonia. It's anhydrous ammonia, so it's pure ammonia, liquefied ammonia that's being sprayed directly onto a farm field, and then you get runoff that goes into a stream, and this is what some of the chemistry that happens. And so this chemical reaction is quite important for these systems. And I have there for you just a little bit of history. I may have talked about this before. The Haber-Bosch process is what produces ammonia on an industrial scale. It's worth Googling that and reading about the history, especially of Fritz Haber, who was a chemist in Germany during the World War II era. It has some infamous, shall we say, elements of his background that you can read about him. I actually like to read a biography of him sometime. But this is the generic process he has for producing ammonia on an industrial scale, which helped to solve a lot of world hunger problems. Now you have a cheap source of fertilizer that can be used worldwide. Okay, so I think that'll be it for this one, but a very practical example of redox chemistry and a practical application out in the environment for the oxidation of ammonia. Good case study.